In the previous lecture, you were introduced to the concept of stress, which is a normalized value of force divided by area in the average sense. And of course, we take the limit of that equation to get an exact value of stress. Now we're going to talk about a concept that is the 3D stress state. After this video, you should be able to do these 6 things. Explain the difference between the stress state and the stress components. Identify the sign, either positive or negative, of a stress component. Interpret and assign stress component subscripts. Explain the meaning of plane stress and recognize when it's occurring. State the relationship between shear stress components on adjacent sides of a material element, and use the partial derivative equilibrium equations to determine whether a given stress state is permissible. So let's start by discussing the stress state. At any point within a body, we can look at a tiny material element, and let's assume that this yellow block is that material element. At each location within the body, we will get a different stress state, which means that the stress state is a field quantity. It's a function of location. And now this little material element could be entirely inside of the material body, which means that all of these surfaces, the 6 sides of an element, are internal surfaces. Or the little element could be near the boundary of a body, and one or more of the faces could be external surfaces. If these are internal surfaces, the stresses that develop on the surface have to do with the interaction of this material element with the adjacent material element. Whereas if a face is on the exterior of the body, then the stress occurs due to applied loading to the surface of the material. The stress state at any point within the body is expressed in terms of 9 different stress components. So I want you to understand that the stress state is an overarching experience of this material, but we express what the material is feeling in terms of 9 individual stress components. And those components, in addition to being based or dependent on the location we're looking at a particular location, if we start to rotate the orientation of this material element, we will get different magnitudes of those components as the vectors start to break up into the different directions, X, Y, and Z, based on being normal or tangential to the surface. There are 9 stress components that completely describe the stress state at a given point. 3 of those are what we call normal stresses. So here we have the 3 normal stresses that are perpendicular to the faces. And on the opposite sides of the cube, you would have equal and opposite stresses. So there's only 3 unique normal stresses. And then we have 6 shear stresses. Each of these represents a shear stress. So 6 plus 3 is 9. It's extremely important for us to keep in mind sign convention when we're looking at stress components. For the normal stresses, if a stress is directed away from the face, that's what we consider positive. So if the stresses are like so, these are positive. Whereas if the stresses are instead facing towards, so if they were facing like so, these would be negative. And on our shear stresses, it's a little bit more complicated. So listen carefully. A positive sign convention is pointed in the positive direction on a positive face. So what I mean by positive face are if you move outward from the material element in the X, Y, or Z positive directions, that is a positive face. So these three faces that we can see are positive. The three faces of this cube that we cannot see, if you were to move outward from those faces of the cube, you would be going in a negative direction, negative X, Y, or Z. So therefore, those are what I call negative faces. So on these three positive faces, your positive shear stresses should be pointing in a positive coordinate direction. So notice that this shear stress is on a positive Y face, pointing in a positive X direction. The other force is pointing in a positive Z direction. If we go to the X face, this is the positive X face, it's now pointing in the positive Y and the positive Z. On the positive Z face, we have stresses pointing in the positive X and positive Y. So all of these shear stresses shown here are positive sign conventions. Our negative sign conventions then would of course be the opposite. So downward, to the right, to the left here, downward, and like so. So these are negative, and the other ones that I drew there are positive. So remember that positive sign convention, on a positive face, you point in the positive direction. On a negative face, you point in the negative direction. And that's really also true of the normal stresses, except that it's much easier just to think if I'm going outward from the cube, I'm positive, and inward, I'm negative. But the plus plus and the negative negative will always, I'm sorry, I think I'm misstating that. Positive sign convention, positive direction on a positive face, and negative direction on a negative face. If you ever have a combination of the two, say a positive direction but a negative face, that's when you get negative sign convention. So it's just like multiplication. Multiply two positive numbers or two negative numbers and you get a positive. But if you multiply one negative and one positive, you get a negative. If we look at specifically the YZ plane, so in this case, we're looking at this face here. That face is contained in the YZ plane with the X coming out towards us. If we look at the normal stress on that plane, we call it sigma XX, where the first X is indicating the direction normal to the plane. So I told you the X direction is the direction coming out towards us. So that first X is the direction normal to the plane on which the stress is occurring. And the second X is the direction of the actual stress. Right, so the second X is because the force is also pointing towards us. So to count the definition of that normal stress then is the limit of that force that's pointing in the X direction divided by the area of that base. Similarly, the shear stresses, there's two of them. Each of them are acting on the X face. So the first variable is X, but they are acting in two different directions. One is acting in the Y direction and one is acting in the Z direction. So tau xy is calculated as the limit of the force in the Y direction divided by the area, right? Y and Y, whereas tau xz is calculated as the force in the Z direction divided by the area. And we can see similar things here when we have a plane that is in the YX or XY plane. Z then is the direction normal. So this is the normal direction to that plane. Therefore, the normal stress, sigma, is signified by ZZ. Both the force and the normal direction are the same. We're looking at the force in the Z direction. And then our shear stresses, they're both acting on the z normal direction. So therefore, we have z as our first subscript. And then the second subscript has to do with the force direction. So if the force is acting in the x direction, it is sigma zx. So that would be this component here, pointing in the x direction. If it is tau zy, that means the force is pointing in the y direction. So that would be this one here, pointing in the y direction. And lastly, we can look at the xz plane, right? We have x pointing this way, z pointing that way. And that means that the normal direction is the y direction. Here we have our normal stress is sigma yy, both the plane and the force. Plane normal and the force directions are the same. The two shear stresses occur on a plane whose normal direction is y. But then one of them is pointing in the x direction. The force used to compute that stress is pointed in the x direction. So that would be this force here pointing in the x direction. And the other stress is pointing in the z direction. So this stress here pointing in the z direction. So that's how we label our stress components. The first subscript is the direction normal to the plane on which the stress occurs. The second subscript is the direction of the stress, which is the same as the direction of the force being used to compute the stress. Now, when the two subscripts are the same, for example, sigma yy, we oftentimes will leave one of those off and simply say sigma y, because it's clear that because sigma is a normal stress, the normal direction and the force direction will be the same. So if you just see sigma y, you know that that is the same as sigma y. When it's a shear stress, we always need both subscripts so that we know which face we're looking at and which direction we're looking at. There's a very special stress state called plane stress, and it occurs when all the stresses are directed perpendicular, it occurs when all the stresses that are directed perpendicular to the plane are zero. So for example, if we're looking at an XY plane, so XY being X and Y plane, so that'd be something that is parallel to this face. And I'm saying that all of the stresses perpendicular to that is zero. So that means this shear stress would be zero, that shear stress, this normal stress, and the other thing that is not stated there, but is important, is that these stresses that occur on a face that is normal to that direction are also zero. So when you're dealing with a plane stress state, the only stresses that should occur are the normal stresses in the plane. So you should have a normal stress in the x direction and a normal stress, oops, I am drawing those reverse what I'm saying. Normal stress in the x direction, normal stress in the y direction, acting on your x and y faces respectively. And you should also have shear stresses. This would be tau yx, and this would be tau xy. Those should be the only stresses that are non-zero. And furthermore, we assume that they're constant through the thickness of the material, which means that from here to there, we assume, or this is rather a material element, but let's say there's a couple material elements next to each other. We would assume that across this whole thickness that they have the same value. So these stresses, tau xy, tau yx, sigma y, and sigma x, they are only a function of x and y, not a function of z. Now we oftentimes will draw this in 2D because it's simpler. So if you see a square like this with stresses, these can be positive or negative, acting on the cube, and then say shear stresses like this, this would be a plane stress state. This is our x, this is our y. So this stress here is that one, except that I've drawn it as a negative stress on the right-hand side. This stress here is sigma y. And then we have our two shear stresses, which are here and here. So these two represent the same thing. All right, now let's take a look at moment equilibrium on a small material element. And when we do that, we're going to discover something about the shear stress components. So if we look at the stresses in let's assume plane stress, we have sigma x, sigma y. I'm drawing them in the positive orientation, but they could be positive, could be negative. And then we have tau xy and tau yx. Down here we have, once again, tau xy and tau yx. It would help if you had coordinate system. There's x and y. So these are our positive faces, and these are our negative faces. Okay. And we want to take the sum of the moment equal to 0. We need to choose a point to take the sum about. We're going to select a point right here in the middle, and we will call it x, comma, y. And we need to define the size of this cube in order to do these calculations. So we will say that this dimension is delta x, this one here, delta y. And then what we can't see in a 2D image is the idea that there is depth to this cube. So if there's depth, that would then become delta z. All right, let's go ahead and do our math. So the sum of the moment is going to be equal to tau xy times the area that it acts on, right? Because if I'm calculating the sum of a moment, I need a force times a distance. In order to get a force, I take a stress times an area. So times delta y, delta z, that would be this face here. Then the distant moment arm is going to be delta x over 2. And this happens twice because we have a tau xy on one side and a tau xy on the other side. And it's a positive moment because our z coordinate axis must be coming out this way, which means that those two are creating positive moment, assuming positive stress. Our tau yx terms, however, are creating negative moment. They are acting on a face whose area is delta x, delta z, and the moment arm, this distance here, is delta y over 2. And once again, there are two of them. We have one up top and one down low. And we all know that this equals 0 because in statics, when we have forces in equilibrium, everything equals 0. All right, so if we go through and take a look at these equations, we can see that dividing everything by 2 gets rid of those 2's. Multiplying by everything by 2 gets rid of those, or you could have just seen that that 2 and that 2 are going to simplify to 1. So that leaves us with delta y times delta z times delta x. And here we have delta x, delta z, delta y. So those are the same, which means if we divide this whole thing by delta x, delta y, delta z, all of these terms leave. And what we're left with is an important finding. Tau xy equals tau yx. So what that is saying is that stress components on two adjacent sides, shear stress components on two adjacent sides must be equal and opposite. So this stress component here, tau yx, is the same as tau xy. And we could have done this with the 3D stress state, except that the other stresses would not have added into this equation. But if we make this a full 3D stress state, and then we look at it by taking the sum of the moments about the x-axis and the sum of the moments about the y, we're going to find the same results, except then it would be tau xz equals tau zx, and tau yz equals tau zy. And because these statements are true, we often only use the terms tau xy, tau yz, and tau xz. We just use the alphabetical order, and so our stress state then would look something like this. Sigma x, sigma y, and then we just say tau xy. And we know that each of these four stresses have the same magnitude, whatever tau xy is. Similarly, we can take the sum of the forces on this material element, and that's going to lead us to some very important equations that I'm calling the partial derivative equilibrium equations. So let's start by drawing our material element again. Sigma x, sigma y. But this time, I'm going to get a little bit more detailed, and I'm going to say that these sigma x and sigma y values might vary slightly across the element. So this element is big enough that we have a slight variation, which means that if this is centered at x and y, then on the left side, we have sigma x at x minus delta x, comma y. And over here, we have sigma x at x plus delta x, comma y. And up here, we have sigma y at x, comma y plus delta y. And down here, we have sigma y at x, comma y minus delta y. So the stuff in the parentheses is just telling you the location, and sigma x is a function of that location, and it's going to vary just slightly over the element. And then we want to add in our shear stresses. So they're all going to be tau xy, except that this one is occurring at x plus delta x, comma y. This tau xy is occurring at x, comma y plus delta y. We have a tau xy on the left face that occurs at x minus delta x, comma y. And then on the bottom face, we have tau xy that occurs at x, comma y minus delta y. And we want to calculate the sum of the forces in the x direction equal to 0. So let's get started. We will start with this component here. So I'll say sigma x that occurs at x plus delta x, comma y. It acts on a surface. Oh, and let me just clarify. Here I've increased the size of the element from the previous slide just to make the equations easier. It's going to get the same result either way, but we're saying that this is 2 delta x now, and this is 2 delta y, and the thickness is then 2 delta z. Okay, so we'll continue. So this now is acting on a cube that has an area 2 delta y, 2 delta z, and it's acting in the positive direction, whereas the negative side over here has a negative direction, sigma x at x minus delta x, comma y, acting on the same area, 2 delta y, 2 delta z. Then we will look up at the top. In the x direction, we have this shear stress. So we'll say plus tau xy. I apologize that for whatever reason the pen doesn't seem to work. We're kind of over in this region. There should be a plus sign. Okay, plus tau xy occurring at x comma y plus delta y. And the surface there has an area 2 delta x, 2 delta z. And now on the bottom face, it's a shear stress component that is acting in the x direction, but it's in the negative x direction. So minus tau xy at x comma y minus delta y. The surface area is 2 delta x, 2 delta z. And one more thing I'm going to add in. This material itself might have a body force. And that body force could be acting in any direction. Could have an fx component, an fy, and an fz. So we'll add that in. We'll say plus fz, where this is the body force. So if, for example, the x direction is the gravity direction, that would be included in this equation. All right, now we're going to divide this entire equation in order to simplify it a little bit by delta x, delta y. Excuse me, that's not what I want to divide by. I want to divide by 8 delta x, delta y, delta z. And the reason for that will become apparent in just a second. So each term has 4 in it, right? A 2 times a 2. So if I'm dividing by 8, all of these terms are going to end up over 1/2. So we'll have a 1/2 times this whole thing. And this, of course, will be divided by 8. Okay, now the dividing by delta x, delta y, delta z means all of these terms go away, but you have a delta, whatever you don't have in that term is now on the bottom. So we have a delta x here, cross out the y and the z, we have a delta x here, we have delta x, delta z, which means this is over delta y, delta x, delta z, this is over delta y. All right, let's clean this up a little bit on the next slide. So that equation should be now delta x, or sorry, sigma x at x plus delta x comma y minus sigma x at x minus delta x comma y, both divided by 2 delta x, plus tau xy at x comma y plus delta y, minus tau xy at x comma y minus delta y, all divided by 2 delta y, plus fx over 8 delta x delta y delta z, and that equals 0. So let's take a look at what we have here. The first part of this equation is looking at the change in sigma x as we go from x minus delta x to x plus delta x. So we're traversing a distance of 2 delta x. And so it's the change in sigma x over that distance. We can also write that as del sigma x del x. So it's the change in our sigma x as we go from one side of the element to the other. Once again, the second part of the equation is the change in our shear stress as we go a distance of 2 delta y, which is from the bottom to the top of the element. So we can say plus the partial derivative of tau xy, and in particular, this is with respect to y, right? First we were traversing in the x direction, now we're traveling in the y direction. Now if we look at this last term, Fx was the force due to a body force, which is a force that acts over the volume of a material. And if we look at our denominator, this is 2 delta x, 2 delta y, 2 delta z, which is the volume of our material. So this term then becomes the body force in units of force per unit volume. So if we define our body force in force per unit volume, we can put that here. And I apologize, I'm using the same nomenclature. Perhaps the other one should have been a capital F for force. This one here is force per unit volume. And this is still equal to 0. We could do the same process on our material element, but do it in the y direction. And we're going to get very identical looking equation. We're going to get the partial derivative of sigma y with respect to y plus the partial derivative of the shear stress with respect to x. But now the body force we're looking at would be the y body force. So these here are our partial derivative equilibrium equations. And they're really nothing more than saying the sum of the forces in the x direction is equal to 0 and the sum of the forces in the y direction is equal to 0, except it's recognizing that our stresses are changing throughout this body. And so stresses, we might have a function to describe that changing stress that we can plug in our coordinate locations into that function and get the stress at any point. And then when we take the derivatives of those stress equations, they must equal 0 when plugged into this equation. So if we take the derivative of the equation that describes the normal stress in the x direction with respect to location, and when we take the derivative of the tau xy equation with respect to y, and then we add it to the body force per unit volume in the x direction, it must equal 0. If you do this equation and it doesn't equal 0, it means that the equations that you have for describing your stress are not permissible. They cannot be physically occurring, because otherwise the object would not be in equilibrium. Because we're looking specifically at a plane stress state, we have two equations, one for each of the two directions that our plane occurs in. If we wanted to look at a full stress state, we would end up with a third equation, and these equations would be have another term in them that would take into consideration that third coordinate direction.